So we derived the Schrödinger equation for the spherically symmetric case, and let's plot the potential as a function of r, so that we can start to determine the solutions. So v of r looks like, let's say, just write the constant like that, some negative c is positive over r, and so that looks like, so this is r, this is v as a function of r, and the potential looks something like that. Right, where we then make it go up to infinity as we approach 0, but plotting that looks like that. And let's say that we want to explore the lowest energy. So somewhere along here we'll have, let me use a different color here. So I want to put the energy, let's call this E naught or E0, that's the lowest energy. And so there's some value here of R, I don't know, R equals A, such that we transition from the potential being below this value and being above it. And these are the conditions that we've seen before. So we have, for our u function, right, the Schrödinger equation is written in terms of the u function, we have an equation that we're familiar with. And so we can write down or draw the u function, which is a solution, and from that we can get the wave function. So if this is that value of r, where we have the transition, and the u function goes to 0 at r equals 0, then here we have to go to 0, and here we must bend toward this axis, right? We must bend this way, but just like for the finite well, we don't go to 0 here, we then transition there, because we are now in this regime where the difference between the energy and the potential flip sign, and so the solution must flip direction and bend away, and we have exponential decrease, something like that. And so we can see that the u function goes like, to be 0 here, we have an r, and here it's e to the minus br for this behavior. And therefore we can conclude that psi, which is u over r, goes like e to the minus br. And so psi of r, the lowest energy eigenfunction, looks like at r equals 0, we have some finite value, so we come down like that. And it looks like that. So now let's think of, in the spherically symmetric case, what happens if we increase the energy. So we're moving to a higher value of energy. So let's just draw it like this. Some higher EH. Well, let's consider the next highest level. Well, that's just some random higher energy value. What does this look like? Let's do the same thing here. Well, we know that we want to add nodes in, right? So we have a u function in this case, which now here's some a, and here it's some a prime, some other value, and So let me just make it easy for myself. We're going to come to 0 here, and we're going to bend more and create a node and continue to bend toward that axis until we get to here, and then we're going to bend the way we bend here because we're now in this region. We're above this value. So the sign flips, and so we then do that from that side. So it looks like that. And of course, the function now looks like, so if this is, I don't know, u0, this is u1. These are, for the spherically symmetric case, this has to go, to satisfy that, we need an r there. And we have some, to get a node there, we have some constant minus r, e to the minus br. We've seen these kinds of solutions before, and therefore what we call in psi1 now looks like u1 over r, which goes like c prime minus r e to the minus br, and that looks like something like that. This is psi 1 of r. Okay, so we could continue to increase in the spherically symmetric case, but there are also the solutions to that are not spherically symmetric, and so we want to go back to the Schrodinger equation and not leave out the theta phi part. We have to go back to that to get the full spectrum of solutions.